All right, welcome back to the second lecture. So before we start, do you have any questions for me from yesterday? Yeah. Yes, there are. Oftentimes, these are non-specific channels that, at least one of the cases is to have a non-specific ion channel, which means it will allow a lot of cations and anions, positive and negative charged ions, to go across. And often one of these channels, so one way to handle these channels is to consider them as a leak, a constant source of current which is open regardless of the changes in the membrane potential. Hmm. I'm not sure I understand the question, so let me try to reinterpret it. It does matter what the ionic selectivity of the channel is. Like for example, we will show that in the Hodgkin-Huxley equation, it is the balance between, or balance or interplay between the sodium and potassium ion, that is what is going to cause the action potential to occur. The non-specific leak channel is going to be a background channel that is constantly leaking current in one way or the other. So it is going to be relegated to the background. And in the Hodgkin-Huxley model, it won't be of a very high magnitude, so it doesn't interfere with the action potential. If it were to happen that if this channel was very large, then it will make it much more difficult for the other channels to form the action potential and things like that. Yeah. Okay. All right. So the program for today is the following. In fact, the program for today and tomorrow, what I want to cover is as follows. I started by giving you sort of a descriptive, a sort of description of the Hodgkin-Huxley model and so on. Today we'll start talking about the equations that correspond to the Hodgkin-Huxley. So here's what I want to do. I want to show you what the equations are, and some of those, and then what eventually I'd like you to do is to be able to do a simulation. So I will show you simulations with the Hodgkin-Huxley. Then we'll do a tutorial tomorrow where you will get a chance to use this package which I will introduce today called XPP which will give you a way of implementing the Hodgkin-Huxley equations, running simulations. And hopefully tomorrow I will show you how to connect two Hodgkin-Huxley neurons, for example, to make a little toy network, right, of two neurons coupled with one synapse. So in principle, those will be the tools that you will have at your disposal to run simulations of networks that you would like. And then after tomorrow, after we've covered, the simulation aspect of, if you wanted to build networks and you wanted to see it, what the behavior is going to be if you put in realistic neuronal-like behavior, that will be a way of, that would be like an electronics engineer having a computer simulation of what would happen if one transistor is connected to one resistor, is connected to a battery, is connected to a bulb. You have that in software, you can do it. That we can do today, right? And so I will give you that facility. I hope to convey that facility to you by tomorrow's tutorial. And we will take care of some of the questions that we've left behind, like where does the Nernst potential come from, work through the numbers to see if you had a potassium concentration different, that would indeed give rise to a Nernst reversal potential and so on and so forth. Okay, so once we are done doing the simulations, in the second half, in the later half of the week, I will step into asking if you had this data, if you had this facility to be able to do simulations, how might you analyze it mathematically? How might you look at ways of understanding what is going on? Typically, these are systems that will be, to step a little ahead of myself, these are systems that are four-dimensional. There are four coupled ordinary differential equations. Ordinary is just a way of saying that these are not partial differential equations, but there's nothing ordinary about them. They're very highly nonlinear differential equations. So there's a lot of complexity that enters into these equations. So we will look for ways to reduce the complexity, and in particular, you reduce the complexity from a four-dimensional system to a two-dimensional system, because the two-dimensional system can be analyzed on the plane. You can look at graphs and you can see diagrams in the plane and see what the behaviors arise from, what sort of geometric structures give rise to the behaviors that correspond to action potentials and so on. When might you have, and so we'll try to look at, when can properties of the neurons be understood from properties of the mathematical system underlying the neurons. Okay, so we will do what is called a phase plane analysis of the neurons, of the equations, right? So that's the program. First, we get the facility to do simulations, right? And some of you will appreciate that, I hope. And some of you will want to do analysis of the equations themselves, and that will be following Wednesday, from Thursday onwards. Does that make sense? And at any point, if you have any questions, feel free to ask me. Tomorrow will be a tutorial session, so it will be completely interactive. I will give you a set of questions, ask you to download and implement the software that I'm talking to. I'll show you how to do it today, and then we'll troubleshoot whatever problems you run into. Okay, does that make sense? Okay, so let's start. So we started by writing down. We started by drawing a diagram of. Right, so that's my model neuron, quote unquote, my point neuron, because think of the entire inside as one point, all of it being at an isopotential. Think of the outside being at ground. Okay, one isopotential for the outside as well. And we decided that we're going to think of the membrane itself as having a capacitance associated with it. So I'm going to draw these circuit elements going between the inside node and the outside node, because that's where I would like to put in my two ends of the voltmeters to measure V in minus V out, right? So I'm going to draw from this node out. I'm going to draw a capacitor, and then, without being too tidy about it, I'll connect the other end of the capacitor to ground, right? Okay. Now, the other thing that we need to account for in this system is to account for, say, a sodium channel. Now, when I say a sodium channel, I don't mean one single protein of the sodium ion channel. I mean the entire population of sodium ion channels that are studying the membrane. Okay, and I told you yesterday why I would think of them as one unit. It's because whatever happens through one sodium ion channel will cause the voltage to change. The voltage will cause another sodium channel in communication with it, will affect the other sodium channel, and in particular it will also affect the potassium channel and so on, right? So the channels along the membrane, even though spatially different, are spatially not in the same position, are in communication through the common variable voltage. Okay, so when I say sodium channel, the physics that corresponds to it, the physical reality that corresponds to it, is all of the entire population of sodium ion proteins that are there on the membrane. Okay, so we thought of this sodium ion channel as a resistor, right? And we will develop the notion in which, the sense in which this can be thought of as a resistor in considerable detail today, right? And let me give you the upshot of what the story is going to be. This is not going to be a passive resistor. This element over here is a memristor. It's not a resistor. It's not a passive resistor in the sense that we knew of before Leon Chua did. Before Leon Chua introduced us to memristors, right? So there's going to be dynamics in particular that is going to be associated with it, and it's not going to be quite as simple as V is equal to IR. It will be V is equal to IR to one extent, and then there'll be other stuff that will also need to be accounted for, and we are going to develop that in more detail. Okay, this is essentially the bit that prevents us from having a neuron on a physical chip right now. Okay. Okay. Now, then there is, so let's connect one of, the other side of it to our ground potential on one side. And the other one, I'm not quite going to connect it up to the node, to the internal node. There is one other element that I should need to include over here. Can anyone think of what might it be? So passive circuits are built of classically conductors, resistors, inductances, and more in a more modern sense, memristances. Okay, don't worry about memristances. There's something else that is often used. Well, batteries. Okay, so I'm going to introduce a battery over here. I'm going to claim that there is actually a battery also. I'm going to displace it away from the membrane, but electrical equivalent circuit that I'm drawing over here represents what's going on at the sodium channel and the entire population of sodium channels. Okay, so that I hope is not getting in the way of understanding what's going on. Okay, I'm representing it just because I need space to draw stuff. I'm representing the battery and the conductance over here as spread out. Okay, okay. So anybody want to think through why include a battery? Hmm. Circulate. Okay, yes, that's a good point. That's a good point. You need a source of energy in there. Anything else? That is correct. Any other reason why might I introduce? So, can you think of this as the Nernst potential of the sodium channel? I remember I told you yesterday. Remember we found that if you have a concentration difference, excuse me, across an ion channel, across a piece of membrane, then the concentration difference gives rise to a potential gradient, and that potential gradient for which the flux corresponding to the concentration is balanced by the flux corresponding to the electrical flow, the electrochemical, there is electrochemical balance, net electrochemical balance, a dynamic equilibrium. That voltage will be called the Nernst potential of that channel. Okay, so if there was a Nernst, if the voltage inside this guy relative to the outside, okay, so I'm just going to call this the membrane potential Vm relative to outside. So if I hold this at Vm and let's say this is 0, if this battery is of a certain value, right, then there won't be any current through this. What is that value of the battery? That value is going to be the Nernst reversal potential. Okay, so this is going to be, I'm going to call it the E sodium. And if it's not clear, that's okay. I will, when we develop the equations, it will become clearer, I hope. Right? So that's essentially what I'm going to have for this. Let's introduce some more notation. I'm going to call the conductance. Conductance is 1 over resistance, right? So if you're used to thinking in terms of resistances, 1 over that is going to be conductance. I'm going to call this the conductance of the sodium channel. That's my reversal potential of the sodium channel. And the two together in series are what comprise the membrane properties of the sodium channel. Okay, now I also need to introduce something similar for the potassium channel because I've got potassium as well in it, in the system. So I'm going to introduce something corresponding to the potassium channel. This diagram is getting terrible, so I will redo the diagram and in some more clarity in a bit. Okay, a very similar sort of thing happens for the potassium as well, and we're going to have to deal with the conductance corresponding to the potassium and then Nernst reversal potential for potassium as well. Right. We can also include some leak channels, the question that was just asked. So this will be a non-specific leak channel. It's just a way of saying the membrane is not perfect. The membrane is going to have some leakage to just any ion that's going across. So we'll include a non-specific current passing through the membrane, just as a resistor passing through with a. There is going to be a battery too. Let me. Yeah, I will put a battery as well. Maybe this will take care of the Nernst potential corresponding to the leak channel as well. Okay. Okay. So that's it. Now let's start writing equations for these things. So let me redraw this diagram just so that it's a little bit clearer. So you've got something. So now that's the diagram that we are thinking of. You can stare at this and convince yourself that that's all I'm drawing. I'm drawing several pairs of conductances and batteries in parallel with each other, one corresponding to each ion channel. This is a non-specific leak channel, and the whole thing is in parallel with a conductance over there. Okay, conductance corresponding to the membrane capacity. I should draw these lines. Okay, I'm not going to be very particular for now about drawing it so that the batteries are with the right signs and all. I'll take care of it in the algebra that I'm going to do. Right? If you wanted me to make sure that the polarity of the battery should be in the right direction and so on, I find it easier to do that in the mathematics when you actually write down the equations. Okay, so now that we have this diagram, can I get rid of the schematic here, or do you want me to leave it up there? Maybe we can get rid of it. Oh, you want to keep it there. Okay, no problem. So let's write down now a diagram, equations corresponding to this. Does anybody want to suggest how might I begin? How should I write down equations corresponding to that? Just start me off and then I'll fill it in. I just want you to think, yeah. In the VM is the membrane potential of the cell. That's what we are looking to express. I'm looking to describe the dynamics in the membrane potential. Yeah. Not sure I understand. So these batteries will determine VM under specific circumstances. And when the VM changes, these conductances will change, which will alter the VM. Yes. I mean, yeah. So whatever currents flowing through it are balanced, yeah, so that VM will remain stationary. Yeah. Any other questions? Okay, so just I want you to hint at how might we start developing equations for this, because I want you to think about what does it mean to go from a schematic in electronic circuit to the model in mathematical terms. Okay, right, that's correct. So this is officially known as Kirchhoff's law. So current cannot be created, current can only be rerouted through the various parts of the circuit. So the net current in the entire circuit is going to be 0. That's the argument that we're going to use to actually start writing the equations for this. Okay, everyone got that? Okay, so let's see. Let me describe it for you first and then we'll write it down. So the current passing through the capacitive current will be C dV by dt, Cm. I put a little notation M over there just to say it's membrane potential, right? And by the way, I am following this book, Mathematical Foundations of Neuroscience. It's a nice book. It's not the only book where these things are developed, obviously. This is due to Bard Ehrmantraut and Dave Terman. It's a very nice book. Covers a lot of neuroscience concepts that go far beyond the stuff that we are describing over here. And authors are Bard Ehrmantraut and Dave Terman. You can always get, come by in the lunch break or something and take a photocopy of, take a photo snapshot of the cover page of the book. Okay, it's a nice book, I recommend it. And if your library has it, that'll be good. It may be a little expensive. I'm not sure if there's an Indian edition to this. But it's a nice book to have, for those, especially for those of you who want to study neuroscience for grad school. Okay, so I'm going to try and stay close to the notation that's developed over here. So yes, I think I have kept it close to that. Excellent. Okay, I might switch from VM to V, but I hope that won't cause confusion. Okay, so let's go through this. Our current through this piece will be, the current, capacitive current is C dV by dt, right? We showed this yesterday. Okay, current passing through this is going to be, if that's the voltage, let's see, the current passing through this will be this voltage minus the battery over here will give you the voltage that's passing through this. So I will write the current through this piece as I L equals Vm minus EL times G L, right? V is equal to IR, or I is equal to GV, which is the same thing, yeah, because G is 1 over R. So the net difference across the battery, across the resistance, will give you the current passing through the current, right, through the resistor. Okay, so we're going to write expressions for all of them in the same way. So IK is going to be GK V minus EK, and so on. So over here, okay, INA is going to be some GNA V minus ENA. Okay, and I'll hasten to point out that in a moment you will see that the GNA, GK that we've written down are not quite as simple as this, because we haven't introduced any voltage dependencies here yet. Right? Remember, I said these were voltage gated channels, right? So bear with me, do not be confused. We will introduce that complexity. It's just not there at this stage, because all I'm doing is I'm writing down Ohm's law, okay? And we will layer on the complexity of it in a minute. But let's just complete Kirchhoff's law over here. So the sum total of all these currents will be equal to 0, right? So I will write it down in this form. Okay, that's my first equation. Okay, convince yourself that I have the right sign right signs in my equation. Right. A good mnemonic to remember this is, I always see this as dV by dt equal to something, and the sign of the voltage on the right hand side must be negative. Right. Imagine a simple exponential decay. dV by dt is equal to minus V. Right. So there should be at least dissipation in the system. Right. Just a mnemonic to remember it. Things work. So with adding up all the sums of currents equal to 0, you get that equation over here. Okay, so far so good. All right, now let's try to layer in. Let's start to layer in some of the complexity that's going to come in from the voltage gatedness of the GN and GK. Does that make sense? Do you see what I'm going to get at? All right, so let's do this. So I'm going to now show you a microscopic picture of what the sodium and potassium channels look like. At the time of Hodgkin and Huxley, this microscopic picture was not available. Hodgkin and Huxley, when they did their modeling, they did not know that the sodium channel looks like what I'm going to draw in a moment over here, right? So I will wait for somebody to raise the question, then how did they get there? How did they develop the equation, right? But let me show you the quote unquote postmodern version of things. Now that we know what the sodium channel looks like, we know what the potassium channel looks like, it's been investigated in detail, we know what the structures look like. Let me show you that version of things. The sodium channel looks like following. You've got 3 proteins. This is the membrane, and I'm going to draw 3 subunits. Think of these as 3 cylinders, right? And if all of the cylinders are in an open position, so let's look at it from the top. Let's imagine you're looking at it from the top. The cylinders could be in an open or a closed position. When they're all strutted out, it opens a pore in the middle, okay, for the ion channels, for the ions to go through, sodium ions to go through. Okay, and if any one of them is in the closed position, then it's not free for the sodium ions to go across. Okay, does that make sense? Is everyone clear how I'm doing this? Okay, also additionally, it's got a ball and a tether that swings and could close the pore, right? So it's a very intense description. You've got 3 positions could be open or closed, right? And you've got an additional ball. Even if these guys are all in the open position, the ball could still come in and close the pore. Okay, so that's what the sodium channel looks like. Potassium channel is somewhat simpler in the sense that you've got 4 subunits to the channel, right? You've got 4 subunits to the channel, and they could be open or closed, right? When all 4 are open is when your pore opens up in the middle and the potassium channel can go through. So we're going to have to write descriptions of this behavior over here, right? These are called gates, subunits or gates. Okay. Just as a, the top view is that all of these, if they're in an open or closed position, which means whether or not the pore is open is decided by that. Okay, so I'm going to write variables. I'm going to write differential equations corresponding to the movement of this, of these gates, right? And here's how we're going to do it. Ready? I'm going to write a variable m, and m is the number of, it's the probability that this subunit of the sodium channel is in the open position, right? Okay? And I'm going to write h for the probability that the ball is in the open position. Okay, the ball is in the unblocking position. Okay, this is called the activation variable. This is going to be called the inactivation variable. Okay, and this sodium current over here, this GNA is going to be written like as follows. GNA is going to be proportional to m cubed h. Can anyone suggest, now that I've given you this diagram, why I would write G proportional to m cubed h? The conductance is proportional to m cubed h. H was the inactivation variable over here. That's right. Right. You're right. There are 3 independent, these gates in this model are assumed to operate independently. So M has to be in the open position, and M, its neighbor M, should be in the open position. When there are 3 M's in the open position, each one of them being independent, is when you get the gate to be open. So you've got M cubed. If M is the probability that each of these subunits are in the open position, then M cubed is the probability that all 3 of them are in the open position, right? Just product of probabilities. You want an event A, and you want an event B, and you want an event C. The probability that all 3 of them occur is the product of these probabilities, right? So you've got m cubed h, and you'd like h. You'd like this h to be such that this pore is conducting, right? So you've got m cubed, but you also need an h to allow for the 1h variable, the probability that the ball is in the unclosing position, unblocking position. You need all 4 events to occur. That's why you got G proportional to m cubed h. All right, does that make sense? Okay, so I'm going to introduce a proportionality constant, Gn bar. That Gn bar is going to be the maximal conductance of the sodium channel. In other words, if m were 1 and h were 1, the product would be 1, and then Gna would be the maximal conductance, Gn bar. Okay. Yes. Okay. Now, can then somebody suggest what my GK is going to be? And I'll call that variable the variable that corresponds to the activation of the potassium channel. I'm going to call that N, that activation variable. So, pop quiz, quickly tell me what would be my corresponding N to the power 4 exactly. Right? Great. So we are almost all on our way here, okay? And L I'm going to just be, I'm just going to allow for GL to be some constant GL bar because it's non-specific to any voltage gating and so on. I'm sorry, which one? Ah, which one? Ah, okay. Okay, so this is a molecule, physically has 3 elements to it, yeah, and these can be in an open or a closed position, right? And on top of it, there is a ball which is tethered to these subunits, which could plug the pore that is forming. Okay, so if I need all 3 of my subunits to be in the open position, and the probability of each one of them being open or not, it's a stochastic process, they're vibrating in their positions, but then the probability has to be m cubed, where m is the probability that each one is in an open position. Does that make sense? And the probability that the ball is unblocking is h. So m cubed h is the probability. Correct. Fair. Absolutely fair. So you are right that as an applied mathematician, you should be thinking about these things. Good question. So I was planning to introduce a tutorial question on this, but let's discuss it right away. You've got stochastically channels opening and closing all over the membrane over here, right? So stochastically, one channel could be doing this, just by random chance, it could be doing something else in a different position over there, right? We did discuss that all the channels are coupled to each other. And there is another layer of stochasticity. I mean, the stochasticity is coming also from the fact that each of the subunits of a particular channel in a location are independent of each other. They could be opening and closing at different rates. Fine? Okay. Now, you can start with a stochastic model and work out from a probabilistic sense an equation, a differential equation for m. I'm going to take another tactic and I will assign the probabilistic version of it as an exercise, okay, for you to take home and work through. There are 2 equivalent ways of going about it. I will show you the version of it that that comes out of a Markov model, okay, but you can actually do it in the microscopic stochastic version that you're suggesting as well. Okay, it will turn out to be equivalent. So let's start discussing that. I'm going to use the following. I'm going to say for the M gate, there is a probability that it is closed and there is a probability that it is open. Okay, what have I done over here? I have gone away from the point of view that I need to track stochastically the ion channel movements of each of the subunits at one location, at another location, at another location, at another location. How am I able to do that? The reason I'm able to do that is if I track the stochastic opening or closing of one of the subunits over here, and I can do it over here, right? This is independent of this. So therefore, by keeping track of one of them, and within each ion channel also, each of the subunits are independent, right? So by tracking the behavior of one of them, one of the subunits, I have effectively tracked the behavior of all of them if I take an average. I have taken an average not only over the individual ion channel, over the 3 subunits of the individual ion channel, but I have also simultaneously taken it over all of the membrane. Right? So I can think of it as a population of independent subunits of the sodium channel. Does that make sense? That population averaging allows me to write down a deterministic model from an underlying stochastic process corresponding to. Hmm. Okay. Correct. That's why you've written m cubed over here. Right? Yeah. I'm asking you, what I'm describing over here is I need to keep track of the dynamics of m itself. Yes. It does, because I want all three of my events to be open. I want all my three of my cylinders to be in the open position for the entire pore to be open. They are independent. There's a difference between being independent and being coupled. So each one is doing something independent of the other two. Right? This motion does not depend on whether this guy is out or in. Right? But I need all three of them to be open for the pore to form. I'm not sure I understand. Maybe we can discuss it after in the break or something, yeah? Because I'll have to think through what exactly your question is. Yeah. 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 It is a conditional probability. And under independence, a conditional probability will be m cubed. Right? Okay. Alright, so here's what I'm going to do. I'm going to take the entire population of subunits and represent it by a Markov variable, by represented in a Markov model by a single variable that corresponds to the probability of either being open or probability of being closed, right? So in other words, I am representing the state diagram of this, of the behaviors here, right? Which means to say, I'm enumerating all possible states that this channel could exist in. So it could exist, the subunit could exist in. So it could exist in a open state, and it could exist in a closed state. Okay, does this make sense? If there were other states possible, I would enumerate those states as well in my Markov model, right? So this is just a general statement about Markov models and so on. So there are channels, and there are sophisticated models of channels where you need not have only two states. You could have other states of partial inactivation and intermediate states that you have to pass through before you go from closed to open and so on. In this model, it's simple. There are only two states possible for each unit, each subunit. Does this make sense? Okay. I will, and if anybody is interested in asking for a more sophisticated model of the sodium channel, let me tell you that it does exist. The independence argument that was implicit or continues to be embedded in the Hodgkin-Huxley equation was abandoned a couple of years ago, and people showed, in particular Patlak showed that you can build a model in which the M and H gates, which we're going to assume are independent of each other, can be coupled, and in fact the results that you get of fitting the data are a little bit better if you do take a coupled model, which says that in reality probably these things are not independent completely, but the difference that you get, the advantage that you get from these things being coupled is not so much in terms of being able to explain the voltage scaling. So one usually goes with the independence argument, right? But if anyone's interested, we can discuss what that coupled model might look like. Right? So I'm going to assume independence as was done in the original Hodgkin-Huxley equation. I'm going to enumerate the states of being open or closed, and then we're going to write down probability or the reaction rates that correspond to the rate at which a subunit is closing and the rate at which the subunit is opening from the open to closed. Okay, so I'm going to try and use the same notation as there in the book. One of these I'm going to call alpha, the other one is going to be called beta, and I don't want to mix them up. Right. So I'm going to call this alpha and I'm going to call this beta. Again, this is a Markov model. You will see Markov models very frequently later in the course, so maybe it's worth spending a little bit of time on this. In a Markov model, once you are at a particular state, right, if there were other states, I wouldn't care about the other states. I only need to care where I am. So it's a state transition model in the sense that if I know the state I am at and I know the transition rate to another position, then that's all I need to know in order to calculate the flux along that pathway. Okay. I don't need to track the rest of the states, right? So it is a local maneuver. It is a maneuver in which you go from being at one state to being at another state. If you're at O and you'd like to calculate the probability that you're coming to C, you only need to look at this B over here. You can essentially safely regard any other state that's there in the model. Does that make sense? Okay, this is a very, very powerful idea. It looks simple because what else could it be, right? No, it's a very powerful idea and it's exploited in many, many, many places, including a lot of positions in, including a lot of fields in mathematical biology, right? And so when you write down I love Markov models, so you should too, is all I can say. Okay, let's write down an equation corresponding to this. Anybody want to suggest writing down? First of all, tell me how many degrees of freedom are there? How many equations should I be writing down for this? 2 states, how many equations? Alpha and beta. Think of this as a population, right? Maybe susceptibles or infected or recovered, right? There would be a rate at which you transition from this population to another population. The population by changing a state, if I'm a channel and I go from being closed to stepping into the open pool, now I belong to a population where things are open. If I can come back into the population where things are closed, right? The rate, how frequently do I step back and forth, are the rates alpha and beta. Does that make sense? Yes? Any other questions? So riddle me this, how many equations should I write for this system? And there are 2 states. So what does that mean? That we write 2 equations, one corresponding to the rate of C and one corresponding to the rate of O. I'm going to write equations of this form, dO by dt. Why would I do this? I would write the equation for dO by dt because I'd like to know what is the rate at which O changes. If O doesn't change, if the population size doesn't change, then I'm sort of done, right? It doesn't matter anymore. Because all I need to figure out is what is the open population, the size of the open population, that's it. How many of these subunits are in the open position? If that's all I needed to care about, I would write down some algebraic equation, fold my hands and be done with it, right? But that's not what I need. I need to know what is the rate at which the open population changes, because the open population does change depending on voltage, right? So in a minute, we will introduce that complexity over here. Alpha and beta are going to depend on voltage. That's what the gating property is. Okay? But for a minute, yeah. That's correct. That's correct. The reason I didn't introduce that equation is you can actually write down Kolmogorov equations and track P of O. In this case, I'm going to represent it as a Markov model, consider the entire population as O, so I'm thinking of this as a concentration dO. Okay, if it makes it easier for you to think of these things, ignore the voltage dependence here. It doesn't matter so much for the development of the equations. We'll introduce it later on and things will be equivalent. I want you to think about how might you go from a model. Again, I stop at those places where the picture is going to lead to the equations, right? So you've got the picture, you've got the biology, now you draw in your boxes and arrows diagram, pause and see how we move into the equations. That's the process of modeling. So give me a hint and I'll take it up. How can I write an equation for whatever this picture is telling me? Sorry, say that again, I couldn't get it. D. That's right, okay, great. So alpha times C minus O, great. Do you want to give us a sense of how you came up with this equation, or what is it that you're invoking? Why did you write this? Yeah, okay. Okay, great. So let's take a look at this equation. If you've never seen this equation before, this is a good position to pause for breath and just work through the content of this equation. The rate at which O changes is going to depend on what? Remember I said it's a Markov model, a state transition model. You have to be at C and you figure out the rate at which you're transitioning to go from this to this. So it's going to depend on the amount of, it's going to depend on the concentration C. Okay, and the rate at which you transition is going to be alpha. So the simplest model is to assume that the rate at which the population O increases is proportional with the proportionality of the rate constant to the population that O is coming from. It is going to be proportional to the amount of C, right? And then there is a flux that takes you away from O, and that is going to depend on how much O you have, right? Because it's moving away from O. So yes, these arrows naturally follow some, a very evocative flow along the arrows, right? So there's a flux corresponding to the flow of C through this arrow into A, and there's a flux that corresponds to the flow of O into C through the arrow B, and we take a simple proportionality. You assume proportionality to the concentration as the size of your flux. Okay, so this makes sense. Now my other question: how many should I just write down one more for dc dt? I could, I should. Yes. Okay, right. Not zero. Yeah, fair enough. So I could write out a second, but remember this. There is something that I ignored over here, and that is that the total population in O plus total population in C is going to be some constant C0, right? Because you're either closed or you're open, right? There's nothing else. So that constraint that the total size of the population is either, all of the population is either in the closed or in the open, introduces a constraint equation into your system. So I in particular will do this like this, okay? And I'll leave it as a quick short exercise to you to show that if you do have a constraint like this and you write down a second equation, that second equation is going to be redundant. You'll get the same thing that you get from writing down the first equation together with a change that I can make over here. I can simply say if this is an equation O, I might take C0 minus O. Over here to C0 minus O will be the C, right? So this equation is written entirely in terms of O alone. So there is only one variable that you need to track, which will give you C and O together because the total is constant. Okay? Right. Second exercise, another good piece of investigation to carry out. These are all math biology tricks which you should have under your belt. The other thing that you can do is I can write down C0 to be equal to 1. Why? This is not a hack. Anybody want to suggest how I can do that? Okay, yes, I am not using a probabilistic version, so I am going to look for another answer. Non-dimensionalization does what? But why? What is the basis of that? That's right, right? So I can always divide by C0 everywhere in my equations, and whatever is my total population size, I normalize everything with respect to the total population size, in which case the new interpretation of this O, which I should have done more carefully, but I just sort of stuck the same symbol for, is that O is a fractional quantity, a fraction of the total population size that is in the open state. Okay, so O's and C's are now the interpretation. The interpretation is that this is a fractional size of the population that's in the open or closed state. Does that make sense? Okay, so carry this out a little bit carefully. I'll leave it as an exercise for you to do. If you were to start with the equations C plus O is equal to C0, what would that mean? And then if you divide by C0, what would that mean? You would actually have new variables, right? You would have like O tilde is equal to O divided by C0, which I am dropping the tilde off and just without loss of generality calling O. Okay, so now we think of these as fractional population sizes. Okay, now let's reintroduce our alphas and betas into this, our voltage dependencies into the alpha and beta. Okay, now this is going to be my equation. I am going to Now explicitly write down that the rate of transition alpha and beta are going to depend on voltage, and we will spend quite a bit of time trying to figure out what this does to our equation. Right? I will also so that's my basic format. So why don't I where should I do this? I'm going to have to erase this now. Okay, I'm going to continue this stuff over here, right? I'm going to write down therefore equations for what do I have to write down equations for? This is the basic format, right? I have got 3 variables that are involved in controlling the subunits of the sodium and potassium, right? So I should write down how many equations? Help me augment this system. We've gotten to the point where we have the M's and the H's and the N's are in our equation. And this is the basic scheme for how subunit dynamics works. So help me write down the equations for the subunits of the sodium and potassium. So I will write equations. Get me started and I'll write down the rest. I should write equations for what? What's that? dm by dt, that's right? So dm by dt, I'll have d, what else? dh by dt, and I will have dn by dt, correct? Those are the subunits of, this is the activation variable of the sodium, that's the inactivation variable of the sodium, that's the activation variable of potassium, right? The 3 subunits of the things we care about in the Hodgkin-Huxley model. Each one of them will be written like so. So let's write them down. I will call it alpha, but now I'll stick a subscript just to say this is the alpha corresponding to the transition rate of the M subunit. This will again be dependent on V 1 minus M minus beta M of V times M. Is everyone okay with this equation? Yeah. Does that make sense? Everyone okay with this? Okay, we'll just complete the rest of them. Alpha H of V 1 minus H minus beta H of V times H. Correct? That's and alpha n of V 1 minus n minus beta n of V. The alphas and betas, we are retaining the common notation because those are the rates of transition as we have described them, and I'm sticking the subscript n, h, or m depending on whether I'm talking about the activation. I'm going to talk when I'm talking about the mu subunit or the h subunit or the n subunit and so on, right? That's the set of equations. So this is equation 2, this is equation 3, this is equation 4. There you go. So we've written down the structure of the equations that correspond to the Hodgkin-Huxley model. Now what do we need to understand? So at this point, Hodgkin-Huxley, when they wrote this down, what they need to understand is, well, what is alpha m, beta m, alpha h, beta h, and alpha n and beta n, correct? And of course, you have to figure out values for this and this and this. Those are the parameters that go into it. Also, you have to figure out what these maximal conductances are and so on, right? It's a massive job. So let's take a step back and ask what kinds of experiments or data would you carry out if you were an experimentalist or if you were asking a collaborator to carry these out for you, that you could discover this? Do you understand the question we are asking? We've written down the functional forms of the equations, right? It has been motivated by writing down electrical equations, building an equivalent electrical circuit, and from that we pushed it as far as we could go to figure out the equations. What remains to do is you have to figure out the parameters of the equations. You have to also figure out what this function is. This is a function, This is an algebraic function in V, so you need to figure out what these could be, right? Uh, yeah. Hmm. Yeah. 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 Correct. Yeah. I mean, though the equations were there, they discovered this cube power as purely as a fitting exercise. That was their best fit, and so then they when they interpreted their equations afterwards, they actually postulated that there must be a single file along which these ions are traveling across. That's their version of saying that this is an ion channel. Yes, yes. The exact equations are these. It was a brilliant piece of work. Rightly won the Nobel Prize for it. And that is the formalism we continue to use, even though we know that there are nuances that can go beyond this, right? For example, the form of the driving force that you write over here, it is a hack between writing an Ohm's law and writing memristive equations for the gating variable and so on. It is possible to go beyond that. You can write equations that are closer to the physiology, physics, biology than just these equations. So, but it is so elegant that I think we continue to follow it. Yeah. Opening, because you want m cubed h to correspond to the opening of the. Okay, I will show you. I will actually, these expressions will be somewhat tedious, so I will just write them out for you. I'll give you one expression and I'll give you a file in which all of those expressions are there and the numbers and so on. It'll take us too far away to try and show everything how how are these things developed in great detail. I'll give you a reference if you're interested. In working through the details, but I will tell you what sort of experiments were done in order to derive these. Okay, these experiments are called voltage clamp experiments, and these are done today as well, right? This is how people do them even today. So this is by no means only a historical anecdote. Okay, so the voltage clamp experiment is the following: you take your cell, and I've already showed you, how to construct a point cell and so on, right? So we won't worry about the details of sticking in silver wires and things like that. Excuse me. Okay. Now, one thing could be to measure the membrane potential Vm simply by holding the cell at whatever it is. I mean, letting the cell be, not stimulating it, and then measuring using a voltmeter what the inside versus outside potential is. Right. The other thing that one is able to do, what was already in the hands of Hodgkin and Huxley, is to actually create an electrode which penetrates the cell. Now the cell is a very lovely thing. The cell membrane, if you do it carefully enough, a very sharp electrode punctures the membrane potential, and goes right through and sits in there. The cell is fluid, it's a little flabby thing, and done carefully, this needle just penetrates it and sits there. It doesn't rupture the cell doesn't explode and things like that. So you can do an intracellular penetration. You can have an intracellular electrode, and using this electrode, you can hold the cell at any potential that you want. That's called a voltage clamp. Clamp because you are clamping the potential of the cell. You'd say, why would you want to do this? Well, this is a very clever technique. You start with some initial condition, and then you hold the cell, this clamping potential Vc, to some value that you like. Right? That will obviously force some current through it. You can also hold the cell at another membrane potential, and these will give rise to currents that will form, and that is your data. You record the current that you would get if you were to hold the cell at the constant potential. If the membrane potential is held constant at a given value, that will give rise to some current response. You switch it, it will give rise to another current response. That data that you get, the currents that correspond to the voltage clamp, are the currents you use to fit these equations. That's your data, and what Hoskin-Huxley did in a brilliant piece of detective work is to back out the equations that would give rise to these currents. Brilliant piece of work, really remarkable. Okay, and that is also what is done today. So a lot of people, a lot of electrophysiology labs develop, good means for doing these things. It's very, very sophisticated, of course. This is just the basic idea behind it. Okay, you can, if anyone's interested in exactly how do you hold a particular voltage at a given level, we can discuss it over tea or so. It's a fairly, in principle, simple argument. Obviously, there are details if you were to do it in practice, but it cannot be. It's not very hard to conceptualize what that might do, right? I should also mention that there are things called current clamps where you inject and hold a certain amount of current in the system, and then you ask what is the voltage response to holding it at that level of current. Right? So there are also current clamp experiments in addition to voltage clamp experiments, and by a judicious use of the current clamp and voltage clamp, you can understand a lot about the dynamics of this. So a lot of electrophysiology rigs are designed to do these in very, very sophisticated ways. In particular, you might start out by holding it at one voltage and then switch it down to another, switch it up to another voltage holding patterns, or by. So there is another point to mentioning this. If you want to investigate the behavior of a system, you're going to have to perturb it, right? Oftentimes, that's a very good way of discovering the properties of that system without taking it apart. If that system is already in place and you would like to understand its properties, one, as a general rule, as a principle, one would perturb the system, look at its response, and build a model which can explain that response. That is something that is done not only in electrophysiology, that is done elsewhere. I'll give you an example. In the early 70s, I believe, the techniques for holding people's glucose at clamp levels was developed. There are things called euglycemic clamps and so on, right? So there's lots of good facility that were developed several decades ago to understand how a person's glucose is cleared away. In our bodies, glucose is maintained at a homeostatic level, which means that in response to food, our glucose goes up, but then it comes back down to normal levels. And it has been a mystery how you bring it back down. How does the body bring it back? Ostensibly, of course, there's insulin acting and there's other hormones and they will all bring it back. But the mystery of it lies in when these processes, these natural processes of the body are disrupted, one doesn't know why they got disrupted, right? So homeostasis is such an important, glucose homeostasis is such an important aspect of human physiology. We've known about it for thousands of years. Charak Samhita and Sushruta Samhita, which we saw yesterday, actually does have mention of Madhumeha. Okay, but I'm going too far apart. But modern techniques do use clamp methods even in understanding things like glucose physiology, which is an all-body physiology, if you think about it, right? It's not an isolated experiment in a lab, not an experiment on an isolated neuron in a lab, right? So these are just very powerful techniques that people use. You'll see things of that sort in gene knockout experiments. You alter one gene and you ask, can I write down a model which will explain the downstream effects of knocking out or knocking in a particular gene in this network of genetic behavior. Okay. Okay. So so they did voltage clamp and current clamp experiments themselves, and those are the equations that they wrote down. Let's see where we want to go from here. I will give you. I will postpone writing down these equations in their details because I will do that as an exercise when I show you how to simulate these things. We will, otherwise I'll just be spending time writing on the board. Right? I will give you the equations in the form of a simulation file. Let's walk through this though to try and figure out how might these equations sort of give you the action potential. After all, that's the holy grail. We want to understand how the action potential arises. We've written down the equations, but now we need to understand it. Okay. So let's go through that. So I'm going to take one of these equations and I'm going to write it also in an equivalent form. dm by dt, if I write down alpha 1 minus m minus beta m I'm dropping the voltage just for making it easy for me to write. I can write this as alpha m minus alpha m plus beta m, and then I can pull out alpha m plus beta m, and I write alpha m right, which I can write down as alpha m over alpha m plus beta m minus m, okay, I should put a little bracket over here, divided by 1 over alpha m plus beta m. Can everyone at the back see what I'm doing? Okay, this I'm going to write down as m infinity minus m over tau m. Okay, and these are, remember, these are voltage dependent quantities. Okay, I've just rearranged this equation to say that I will have m infinity minus m over some quote unquote time constant of this equation, right? The reason to write this as m infinity is saying that for steady state dm by dt is equal to 0, m will essentially have to be m infinity. Okay, so this is just an alternative form people write things in. It makes it a little bit easier to study these equations. Now where should I write these things? Here. I should have started on the left. Wouldn't have to yeah. Yeah, for the activation subunit of the sodium channel. Yes. Yes. They're independent, only coupled through the voltage. People worry hard in sophisticated ways what would happen if you were to abandon this assumption. And one place where this is used very frequently is when you're studying calcium trafficking through channels, and in a lot of places in neurons, in the heart cell and so on, clusters of calcium channels need to be together for the event to accumulate enough to form calcium waves and such like that. So people, that's one place I know where people worry hard about the spatial organization of these channels. Okay. All right, so I'm going to draw a little diagram for you. This is diagram 1.1. I'm going to draw two diagrams actually. So this is going to be m infinity as a function of voltage. Voltage goes, say, between minus 100 to, say, 40 or 50, let's say 40 millivolts. Okay. Can anyone suggest for me why this makes sense? I'm saying the m infinity looks like this. Does this make sense? Yeah. Right. Okay. So does this make sense? This makes sense, right? Correct. So you got a sigmoidal sort of profile, and it generally is monotone increasing. Obviously, by definition, m is not going to be greater than 1 because it's a fraction. Yeah. So the maximum quantity of the fraction is 1. What this says to us is that as voltage increases, more and more channels, more and more subunits at least, of the sodium channel tend to open as voltage increases. Okay, that's kind of important, right? Okay. Now, anybody want to suggest what the H infinity might look like? H is actually an inactivation wave. So, the H actually closes when voltage goes up. So, in the sodium channel, imagine what that might mean. That's saying the M is trying to open, as voltage goes up, the M is trying to open it, that's what's called the activation gate, and the H is trying to close it, and that's called the inactivation gate, right? So these are two opposite effects, taking place within the same channel. It's amazing. But the symmetry is broken. Where is it broken? In the cubed. Everything lies in the cube over here. The thing that is going to happen, and we'll see this in a minute, is the effect of M is enhanced because there's 3 of them. And that is going to be crucial for the channel to actually open. Otherwise, otherwise it's an interplay between one M trying to open it and one H trying to open it, and the channel sort of feels trapped in there. But because there's an M cubed in there, there's going to be an explosive positive feedback that's actually going to allow the channel to open. And when that channel opens is when the action potential is going to start firing, right? So I should tell you also about what the potassium gate is. And the potassium gate is looks something like that. So it is very similar. The potassium gate is going to look similar to that. Okay. Is everyone okay with that? So if I should draw this more carefully, I think. I don't mean to say that this is touching this. I believe it's an asymptote. Okay, and the other thing is now we should draw some taus. Can everyone see this at this position? Yeah? Okay. So I'm going to draw, I should write down some, this is tau in milliseconds. And just to give you some sense of scale, this is on the order of about 10, and this is 0. Okay. And again, voltage is minus 100 to 40. Okay, so the M looks like this, the N looks like this, and H looks like this. Notice that the M, for the broad range over which the action potential actually occurs, say from minus 70 to 40 millivolts, the M is considerably smaller than N and H. What do you think that means? If you look at these equations over here, the tau corresponding to M overall, broadly speaking, this is obviously nuanced with respect to voltage, but sort of take an average value that is lower than the taus of these two. What do you think that means in terms of the equations if you look at it over here? Sort of mentally ignore the voltage dependence. If this were a constant, if that were a constant, what would that tell you from the first order differential equations which all of you can solve? That would mean, think of it as a time constant. The question I'm asking is, which of these gates are going to be the quickest to respond, M, H or N? And look at this diagram over here to try and recover that. It's a sort of intuition that's very valuable in working with models. It's not about the skew. Overall, think of this as being constant. Ignore the skew, ignore the nuance of it. Think of it as some level. I'm saying this level in overall is much smaller, almost an order of magnitude smaller than that level over there. What does that mean for M, H and N? Which of these gates is going to be faster to respond? Which of the M's will be quicker to change? M, H or N, which of the gating variables will be quicker to change? And the hint is over here. But the M subunit itself is the fastest to respond because it's got the lowest time constant over here, right? Work it out for yourself. The M is going to be the one that's going to respond quickly to changes in voltage. Okay. All right. So I think I'm going to show you a simulation here, and it might work best if I just show you all of the equations in the simulation itself. I'll turn on this in a minute. Oh, thanks. Okay, what happened? That didn't help. Bear with me while I turn this on. Okay. Okay. So I want you to stare at this script over here. This is written for the program XPP, which we're going to talk about, and I'm going to show you simulations with. Notice that we are writing it in a format that's very close to writing mathematics as you would write it, right? So these are the equations. You write v prime, n prime, h prime, n prime. Obviously, the primes are standing for d by dt. So this is dv by dt, dm by dt, h and dn by dt. Those are your GNA m cubed h v minus vna terms. That's your potassium term. That's your leak current. Divide by c. C is the membrane potential. And we'll discuss this a little bit later, what exactly this means. It's a way of stimulating the cell, the neuron. The alphas and betas are written as A's and B's, and those are the expressions. I obviously won't expect you to remember them. I've never remembered them in the tens of years that I've been staring at them. But convince yourself that these expressions will give rise to the diagrams that I draw. So it's a nice instructive exercise for you to actually take out a plotting package and see that these expressions do satisfy the sorts of figures that I drew over there, right? Okay, so hopefully you're, once you do that, you will be convinced that these expressions do actually give the picture that I drew behind the screen over there. These are parameters. This is VNA or ENA as I wrote it down in my equations. That's the reversal potential. Notice that the reversal potential is minus 77 and the reverse of potassium, and for sodium the reversal potential is plus 50. So the reversal potential for potassium is negative and the reversal potential for sodium is positive. This will be crucial because of the following reason. If only the sodium gate were open, what do you think? And forget the potassium grade. Let's say there was no potassium grade. You blocked it out entirely. You threw on a potassium channel block, or only sodium gate is there. What do you think will be the potential of the cell if only sodium gates are in there? It will be the reversal potential of sodium. Right? That's when the current will stop flowing, at least in a net sense. Right? So if only the sodium gate were there, the cell would be at plus 50 millivolts. If only the potassium gate were there, the cell would be at minus 77. And the two of them together, through the dynamics of the V and H, will give rise to the action potential. So the swing between somewhere in between the regions defined by the sodium and the potassium reversal potentials, right? You swing between these two. Okay? And the swing is going to happen due to the M, H, and N gates. So let's see how that might happen. Is there anything else about this file that you would like me to describe? There's a few other things that are placeholder things, just housekeeper stuff. Yeah. It's a complicated form. Okay. So at the time that Hodgkin and Huxley did it, they used these complicated forms. And post Hodgkin and Huxley, people have tried to explain where these potential forms could come from, where these forms could actually come from. It turns out that one of the theories is that in the transition rates from going from between the open and closed, those expressions are simply exponentials in voltage, right? And there are theories of how channels function, like the iron gate theory and so on, or there are free energy landscape theories of what goes on inside a channel where people have tried to explain this from the biophysics of it. Why would it be that the transition rate is an exponential, a pure exponential in voltage, right? But just by taking that simple argument that the transition probability of going from one side to the other is an exponential, all of these things are built up. It's no more complicated than that, even though it looks complicated in this form as it's written. Okay? Excuse me. Okay, anything about this that you would like me to? This is just some housekeeper stuff which allows you to track these, and we'll do this in a tutorial tomorrow, so you don't have to worry too hard about it, right? Just know for now that these are the equations, those are the functions that correspond to the alphas, alpha and betas for the different channel subunits, and those are the numbers that are there in this. You will notice that there is a this GNA is actually the GNA bar, the maximal conductance that I wrote down, and so on and so forth. C is given as 1 because everything is normalized with respect to this membrane capacity. Okay, and don't worry about the phi. Phi is a variable that takes care of temperature changes. We'll just ignore it for the moment. Phi is set to 1. Don't worry about it at all. You just forget about it. It's 1. Okay, so now I'm going to show you that this actually gives rise to an action potential, and we'll talk about heuristically, not mathematically, but heuristically why this is happening, why that action potential occurs. Right? Okay, so let me start by opening up this program. This is a Windows platform, so I have to set up, not set up, X. I have to open an X server. In this case, I'm using an X server called Xmin32, and I'm going to use just a free version of things, so as to show you that with to some limitations, you can work with a free version of Xmin30. So this is an X server. Those of you who don't work with Linux, just know that this is a program. If you start this up, you'll be able to use a program that was written originally for Linux in Windows. Okay, and of course, if you work with Linux, there are Linux versions of the program that are available, which you should use. They are slightly better, but almost everything that you can do with the Linux version, you can do in a Windows version as well. Okay. Oops, I closed my main window. Okay, so I have set it up so that if I click on this file, it's going to open the program, that XPPR program that I've been talking about. So I'm going to do that. You will, so I want you guys to download this program. I will write down the website from which you can download it. It's a very light program. You all have laptops. Download it over one of the breaks and install it. If there are any difficulties, ask me, but there are very good instructions for installing it. It's a very light program. It's nowhere close to having to install Word or something like that. It's just really light. You can do it in a minute. So that is the program. It opens up and I click. I have already set it up. It's a small step. So it just tells you, Windows will ask you, I've never seen this file before. If you're clicking on it, what program do you want me to open it with? And you find the location of the program, XPP out, and link it to that, and it opens up. Right? It's no big deal. Okay, this is the program that opens up, and we'll talk in detail about the various, buttons. Believe it or not, these are buttons. In the old, Windows, Linux style, these are buttons. So this program opens up. What the program does is it takes that script that you had written and solves those equations, provided you've written them correctly, solves those equations numerically and shows you using a graphical interface what the output is, and gives you a way to tweak some of the parameters and things like that from this interface. Okay, so this gives you a window right off the bat where voltage will be represented as a function of time. So this, if it's done correctly, is the solution of those differential equations with respect to time, right? So this axis is time, that's voltage. So I will show you tomorrow in the tutorial all of the details of how this is done. What I'm going to do right now is just demonstrate that you can do it so that you know what you're looking for. So I'm going to say initial conditions, and I'm going to say go, and something has happened, and I'll show you what this is, okay? So that is the response to the, to what? Let's find out. Let's put this up here. To no current injected into the neuron. it takes a little bit of a tweak, not too much, to add a way of entering current into the neuron. Okay, the diagram that I do, the equivalent circuit that I do, you just have to change, I naught for the current total coming in. The total current won't be 0, it will be equal to some I naught, whatever current you're injecting into the neuron. That's all that takes, right? Okay, so you can do that very quickly in the equations, and if anybody is confused about it, we'll talk about it tomorrow in the tutorial. What I can do then is change the amount of current that's coming into the neuron. So I will change it for you, and I want you to see what happens. Okay, I will change this current from I0 to maybe 5. Okay, I'm going up there, that's the position you're looking for. And I'm going to say click go, and something else has happened, and there it is. Okay. This I0 was changed to 5, and that's your action potential. Okay, maybe I can do this a little bit better, maybe not. It was actually dependent on nuances of the initial conditions, right? So if I try to do this again after having let the neuron relax, it actually doesn't give you an action potential. This actually is not an action potential. Notice the range is minus 61. Minus 61, right? That's just in the large scheme of things, that is not an action potential. So what I'm going to do next is I'm going to increase the current. I'm going to say make it 20. I have no idea what I'm looking for. I'm just increasing it willy-nilly. Okay. Okay, something happened. Oh wow! Now I've got beautiful set of. I've got a whole train of action potential. Not just one. I got boom, 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 boom. I got 4 of them in this time over here. Okay, so this is just a quick demonstration that you do get an action potential with this model. And in fact, if the current is appropriately high, you can get many of these, right? So I will allow you to play around with these kinds of simulations, right? What we'll do tomorrow is, in the tutorial, we will figure out how to stimulate the neuron to get all sorts of behaviors that we'd like it to do. For example, could you get 1 action potential or 2 without getting a 3rd one? Right, that sort of thing. It gives you a facility to play around with these neurons. But let's take a quick look through what is happening in a single action potential, right? So take a single action potential like so. If say the cell was at rest, you give it a little bit of a stimulus, it goes up, swings up, comes below resting, and then comes back up. What do you think is going on in this region over here? Well, what's going on is that the sodium current starts to open up. The voltage goes up, so M infinity, okay, I will have to remove this, but never mind. I'll just describe it to you in words. The M infinity you saw was increasing in voltage, correct? So if the voltage starts to increase just a little bit, the M infinity gates, the M gates, M tries to come close to M infinity, so M infinity is increasing, which means the M gates start to open up. If the M gates start to open up, that allows for sodium to come in. If sodium comes in, what will happen is that the cell will get polarized, depolarized, repolarized. What do you think will happen if sodium comes into the cell? Remember, sodium is high on the outside. Depolarized, that's right. The sodium will start to the cell will pick on a positive potential. What will that do to the M infinity? If the voltage goes up a little bit, M infinity is increasing in voltage, will you start to move towards higher M infinity or lower? You will go towards a region of higher and higher M infinity. Remember, voltage, M infinity goes up. As the voltage goes up, you start tracking higher and higher M infinity. So more M infinity means more of the channels will open. More of the channels open means more voltage goes up. The more the voltage gets depolarized. So this is a positive feedback loop. Boom. The whole thing explodes very quickly, and because there's an M cubed in there, this effect dominates over everything else. And because tau of M was low, so the whole thing becomes fast. I want you to see all of this in the simulations tomorrow. I want you to figure out for yourself, convince yourself that these heuristic ideas do actually mean something. Okay, and if you're not convinced, that's great too. We'll do the math of it, the analysis of it, and then maybe you'll be convinced, right? Depending on the flavor of analysis that satisfies you, both of these can make sense. Both of these strategies and together can make sense as well, right? So the M infinity climbs up. At some point, things are not just going to go on and on. This thing is actually quite explosive. Look at this. It's gone up, like really rapidly climbed up, right? At some point, the H gate kicks in. The H gate remember that the H gate the H infinity is decreasing with the voltage. So when the voltage is really, really high, the H infinity is really, really low. So the H variable is going to track a very low H. And when that happens, the ball will come and close the sodium pore, right? And that means the sodium will stop passing through. If the sodium stops passing through and the voltage is already high, well, it's not going to change anymore. But what if the N gates, the sodium gate, the potassium gate now starts to open? Because remember what the potassium gate was? It was N infinity was up in increasing this thing. So the N infinity becomes high at higher voltage up over there. And that allows for the potassium gate to open. If the potassium gate opens, remember the Nernst potential of the potassium. Nernst potential of the potassium says that the stuff will stop flowing through the potassium channel when you are minus 80 or minus 80, 77 in this case. Right? So then because the potassium channel is open, boom, everything starts to go towards the potassium Nernst potential. Right? Remember that the sodium is inactivated, so it's not going to be very effective. Potassium is active and there's nothing to stop it. So it brings everything down towards its Nernst potential. Right? So the sodium gate essentially is responsible for opening it. The potassium gate is responsible for closing it. And then once you're back down towards resting potentials, well, things are going to relax back to where you started from. Everything goes slowly back to normalization. That's when you get hyperpolarization. After hyperpolarization, come back to rest. Okay? So it's a very beautiful interplay of things happening fast first and then things happening fast in the other direction, or somewhat slower in the opposite direction to normalize everything. So in fact, the effect of the potassium channel is just slightly delayed from the sodium action. And so this potassium channel for this reason is called the delayed rectifier potassium channel. And it's just so there are several nuances of it that we can discuss once you've played with it, but it's just so clever the way this system is set up. Okay, and this entire dynamics of the conductances, the fact that I had to write down equations of this type in determining the conductance of sodium and potassium is what makes this a memristor. You can formally show. Actually, Leon Chua did show in a successive paper, in a follow-up paper from his original paper in which he introduced the memristor, and it's valuable reading in that paper itself. I think it was Kang and Chua who showed it, that the gating variables as represented in the Hodgkin-Huxley equations do form exactly formally the equations of a memristor. Okay. So with that, I think I've run out of time, so I'll close. What we'll do tomorrow is actually study various properties of the Hodgkin-Huxley. For example, what would happen if I were to increase current even more? Would you just get more action potentials? Would you get something else? And so on and so forth. So we'll play around with these questions tomorrow in this, and I will also give you a way of linking one neuron to another neuron through a synaptic variable, which means you will have all of the facilities to make your own networks and simulations of networks of neurons. Okay? All right. Thank you so much.